Hello, so if you're watching this, you probably got the ant simulation pre-release as one of your worries for your A-levels. Quick thing before we start, this video is going to be long, so use the chapter markers and come back to what you need. But if you've got time, make sure to watch it all the way through once and then revisit the sections you need to. So here's how the video is structured. Part 1 is going to be the main menu and how you control the simulation. Part 2 is what the simulator actually does. The biology, the rules, the 4 simulations. Part 3, how the code works. Part 4 is the known issues and bugs in the code. Part 5, the extension tasks and 2 specific problems. And then we'll do theory question predictions and model answers. Let's not waste another second and get into it. The main menu. This is literally the first thing you'll see when you run the program. When the program starts, it runs the main function that's on line 1 of the skeleton code. The very first thing it does is ask you to enter a simulation. If you look at this, the code reads your input as a string, sim number equals input, and then goes through a chain of if-elif statements. If you type 1, it sets the simulation parameter to a specific list of 8 numbers. If you type 2, a different list, and so on for 3 and 4. Those 8 numbers are number of nests, number of rows, number of columns, starting food in each nest, number of food cells, starting ants per nest, pheromone strength, and pheromone decay rate. So for simulation 1, the list is 1, 5, 5, 500, 3, 5, 1050. That means 1 nest, 5 rows, 5 columns, 500 food per nest, 3 food cells on the grid, 5 ants per nest, pheromone starting strength 1000, pheromone decays by 50 each stage. Here are all 4 simulations compared. You absolutely need to know these for the exams. They come up in the theory questions about the grid size, ant count, and the effect of different decay rates. Notice that simulation 1 and 2 are identical except for pheromone decay. Simulation 2 has decay 100 versus simulation 1's 50. So trails fade twice as fast as simulation 2. This means ants lose track of food source more quickly and the colony would struggle more. Simulation 4 is the interesting one because it's the only one with 2 nests. This introduces competition dynamics, and this is why you'd realize some tasks would say this only needs to work for a single nest. Also note that in all 4 simulations, the initial pheromone strength is 1000. There are always 3 food cells placed randomly on the grid. All nests start with 500 units of food, and food cells cannot be placed in the same cell as the nest. However, this is flagged as a bug. Multiple food cells can end up in the same non-nest cell. We'll come back to this in part 4. Once you've chosen your simulation, the program creates a simulation object using those parameters and then drop you into the main menu loop. Line 17 to 47 of the main function. You'd realize this loop runs forever. While choice is not equal to 9, every cell iteration calls display menu, which just prints 6 options. Then get choice, which just reads your input as a string. Then a chain of if-elif statements handles whichever option you picked. Let's walk through each of those options because the exam will ask about these. Option 1, display overall details. This calls the simulation.getDetails function, which iterates through every single cell in the entire grid, row by row, column by column, and builds up a big string showing what's in each cell. Whether that's a nest, how many ants, how many pheromones, how much food. It prints that string. This is your bird's eye view of the whole world. The getDetails function has 2 nested for loops. Outer for loops goes through row 1 to the number of rows. Inner loop goes through column 1 to the number of columns. For each cell, it calls getIndex to find it in the flat list, then checks for nest, ants, pheromones, and the food. Only things that exist get printed, the zeros are hidden. Here's something really important about the getDetails. Look at the grid display. It uses 1 based indexes. So row 1 and column 1 is the top left. The grid goes to 5, so column 5 and row 5 for simulation 1. That's why the loop are ranged from range 1 self dot number of rows plus 1, not 0 to self number of rows. If you ever write code that loops over the grid, you must use 1 based indexing or everything would be off by 1. So option 2, display area details. This will ask you for 2 cell references, a top left and a bottom right corner of the rectangular area. It calls get area details, which work exactly the same as the get details, but only iterate within your specified rectangle. Really useful for zooming in on parts of the large 10 by 10 grid. Notice the end row plus 1 and end column plus 1. You'll realize the plus 1 is for the exact same reason. Python's range is exclusive at the top, so you'd need the plus 1 to include the last row or the column. The inspect cell. This is the most detailed view. You specify one specific cell and it calls the get cell details. Unlike the other two, this one shows the individual details of every ant in the cell, their ID, type, age, and every pheromone, which ant it belongs to, and its current strength. Note the pattern here. To find ants in a specific cell, it loops through all ants in the entire simulation and checks A dot in same location bracket current cell. That's really important. There's no shortcut, and same for the pheromone. This is actually one of the known bugs we'll discuss later. Because of where the new line is placed, not all ants always display correctly. Advanced 1 stage simply calls the this simulation.advanced stage bracket number 1. We'll look at what advanced stage actually does in part 3, its most important method in the whole program. Advanced X stages. It reads the integer from the user, calls the simulation.advanced stage number of stages, same method, but it just runs the loop more times. Option 9, quit. The while condition is choice not equal to 9, so entering 9 breaks the loop and the program ends. One more thing about the main program before we move on, the random number generator. Right at the top of the skeleton code, you have import random. The whole program uses Python's random module, a single shared random number generator for the entire simulation. Why? If you kept making new random generators, especially quickly, they might get seeded by the same system clock value and produce the same numbers repeatedly. So one shared generator gives one continuous non-repeating sequence. Again, this could come up in the theory questions. Right, part 2. What is this simulation actually modeling and why does it behave the way it does? The simulation models an ant colony surviving in a grid-based habitat. The grid is the world, a 2D array of cells, each of which can contain nest, food, ants, pheromones, and any combination of those things. The simulation only considered 2 types of ants, queen ant and worker ants. There aren't any soldiers or drones, but those are the kind of additions they might ask you in the exam. Queen ants never leave the nest. Their only function is to reproduce, and even that is probabilistic, only happening when the nest has plenty of food. Every nest always has exactly 1 queen at the start, though more can be born. Worker ants do everything else. They leave the nest, wander around the grid, find food, carry it back, and drops pheromone trails as they go. They are the ones doing all the work, hence the name. Here's how the real ant colony algorithm actually works, and the simulation copies this faithfully. A worker ant starts at the nest with no idea where the food is. It just wanders randomly, picking a neighboring cell at random each stage. If it happens to stumble on a food source, it picks some up to its carrying capacity of 30 units, and immediately starts heading directly back to the nest. And as it walks back, it drops a pheromone in each cell it passes through. Now, other worker ants that are out searching and happen to pass near the pheromone trail gets attracted to it. They move towards the strongest pheromone signal they can detect. They follow the trail to the source. They pick up the food, come back, and then reinforce the trail. Over time, you get this motorway of ants going directly between nest and food with no central planning at all. But here's the clever part, the pheromones decay. Each stage, every pheromone's strength is reduced by the pheromone decay value. In simulation 1, that's 50 per stage. So pheromone with initial strength of 1000 lasts 20 stages before disappearing. In simulation 2, with a decay of 100, it only lasts about 10 stages. This decay is very crucial. It means if a food source runs dry, the trail to it naturally fades. Ants stop being attracted to an empty cell. The colony self-corrects. No ant has to decide to abandon the trail. It just happens through the decay. And a shorter trail gets reinforced faster because the round trip takes fewer stages. So more ants are walking it per unit of time, each one topping up the pheromone strength. So the colony naturally optimizes towards shorter, more efficient routes. The nest actively manages the colony. Each stage, every ant belonging to a nest consumes food from it. Queen consumes 10 units per stage, worker consumes 2 units. This happens even if the workers are foraging away from the nest. If there's plenty of food and the food level is at least 5 times the number of worker ants, then the nest is healthy. The queen has a 50% chance of giving birth to a new ant. If a new ant is born, there's a 2% chance it's a queen ant and a 98% chance that it's a worker ant. So the overall chance of a new queen per stage is only one person. If food gets low, ants get culled. The culling logic is layered. Up to 3 ants can be culled in a single bad stage. And there's a bug in the code that we'll discuss. The culled ants are selected from all ants in the simulation, not just those belonging to the starving nest. And here's something that confuses most people. In all 4 simulations, there are always 3 food cells placed randomly. Each food cell starts with 500 units of food. The nest also starts with 500 units. Those are separate. So the nest food is what ants bring home. Cell food is what's out on the grid waiting to be collected. Because food is placed randomly, it's possible for 2 food cells to land in the same grid square, and you'd see 1,000 food in one cell. This is flagged as a bug in the code, and we'll come back to it. The first nest is always placed at row 2, column 4, and that's hard-coded in the simulation constructor. For example, simulation 4 has 2, are placed at random valid position. Part 3, how the code actually works. This is going to be the meaty bit. Before we look at a single method, understand the shape of the whole program. Everything's running on this class hierarchy. At the very top of the inheritance tree is entity. Entity is the base class for almost everything in the simulation. An entity simply knows where it is. It has a row, it has a column. It also has an ID set to none initially. Entity has an advanced stage method that does nothing. It's a placeholder meant to be overridden. And a get details method that returns an empty string is the exact same thing, which would be overridden. From entity, 4 things inherit: cell, nest, ant, pheromone. And from ant, 2 more things inherit: the queen ant and worker ant. Then there's the simulation class, which doesn't inherit entity. Simulation is the orchestrator. It holds list of everything else. It has the self.nest, self.ant, self.pheromones, and self.grid. It knows about everything, and everything else only knows about itself. This would matter enormously for the exam. So when you're asked to add a feature, you need to know which class has access to what. If your feature needs to know about both an ant and a food cell, it has to live in simulation, because simulation is the only class that can see both. Let me highlight the most useful method on entity: in same location. This takes another entity object and returns true if they are at the same row and column. You'll use this constantly. Checking if an ant is at a nest, ant.inSameLocation nest is used. Checking if a pheromone is in a particular cell, pheromone.inSameLocation cell. It's a lot more cleaner than manually comparing rows and columns, the grid. This is the one thing that confuses almost everyone at first. The grid looks 2D when it's displayed. You see row 1, column 1, all the way to row 5, column 5 for simulation 1. But internally, it's stored as a flat one-dimensional Python list called self.grid. Why? This is a common technique in programming. One list is simpler to manage than a list of lists. The private method getIndex does the conversion. The formula is row take away 1 times number of columns plus column take away 1. The minus ones are because our grid is 1 based indexing. So rows and columns start at 1, not 0. And so for a 5 column grid, what's the index of row 2 and column 5? Feel free to pause and work that out. It's going to be 2 take away 1 times 5 plus 5 take away 1, which is going to give us 5 plus 4, and that's 9. Now let's talk about the neighbor detection, because this is central to how the ants move. The private method getIndices of neighbors return a list of 9 values. The grid indices of all cells in the 3x3 neighborhood around a given cell, including -1 for cells that do not exist, so are essentially out of bound, or the cell itself. For a cell at row 3 and column 2 in a 5x5 grid, it would return 5, 6, 7, 10, -1, 12, 15, 16, 17. The -1 at position 4, index 4 in the list, corresponds to the cell itself. For a corner cell like row 1, column 1, most neighbors are out of bound. You'd get mostly -1s for only 3 valid neighbors, the cell to the right, below, and diagonally right above. For row 1, column 1 in a 5x5 grid, the valid neighbor indices are at position 1, 2, 2, 1, and 2, 2, which correspond to grid indices 1, 5, and 6. The full returned list would be -1, -1, -1, -1, -1, -1, -1, 5, and 6. Now the most important method in the entire program: advanced stage in the simulation class. Every time the simulation moves forward, this is what runs. It happens in 3 phases, strictly in order, and understanding this order is really essential. So phase 1 is the pheromone decay. The method builds an empty list called pheromones to delete. It then loops through every pheromone, calls advanced stage on each one, which subtracts the decay rate from its strength and clamps to 0. If the strength hits 0, it goes to the deletion list. It goes on the If the strength hits 0, it goes on the deletion list. After the loop finishes, a second loop removes those pheromones from the main list. Now, why is there the separate deletion list? Because you cannot remove items from a list while you're iterating through it. If you tried to do self.pheromone.remove inside the for loop, you'd get unpredictable behavior. Items would be skipped. This two-pass pattern is the correct solution, and it could come up in your own code writing. Phase 2, ant turns. Every ant gets to act this stage. For each ant, the simulation checks a priority chain of conditions. First check is that the ant's carrying food, and is it at its own nest? If yes, deposit the food. Call add food to nest with the amount, then reset the ant's food to 0 with a.update food carried. Second check is the current cell's food greater than 0, and is the ant carrying nothing, and does the ant have food capacity above 0? That's the third condition. Third condition, a.get food capacity greater than 0, stops certain ant types with 0 food capacity from accidentally picking up food. If all three conditions are true, the ant picks up food. A random amount is chosen between 1 and the ant's capacity, but then adjusted in a while loop to make sure it doesn't exceed what's in the cell and does not put the ant over capacity. A simple for loop calls n.advanced stage on every nest. This hands off to the nest classes on advanced stage method. Let's look at nest's advanced stage in detail. First, there's a null check. If somehow there's no ant at all, skip everything. Then it counts up food consumption. A for loop through all ants. If an ant's nest row and nest column match its nest row and column, it belongs to this nest. Queens contribute 10 to count. Worker contributes 2 to count, and workers also increment ants in nest count. Just note that this counts ants that belong to the nest, not ants physically in the nest right now. A worker ant out foraging miles from the nest still costs 2 food per stage from its home nest stores. After the loop, self.changeFood integer count deducts the total. Change food clamps at 0, so food level can never go negative. Then there's the culling check. 3 stacking conditions. Each one can add 1 to ants to cull. So condition 1 is food is 0 and they are workers, cull. Condition 2 is food is less than the worker count, cull once more. Condition 3, food is less than worker count times 5, cull one more. Maximum 3 ants can be culled in one stage. Then there's a safety check. If ants to cull would exceed the actual number of workers, then it's capped. Now let's look at an example calculation question. So for this question, food level 7, there are 10 ants. Is food 0? No. And the next check would be, is food less than the worker count? 7 is less than 10? Yes. Ants to cull becomes 1. Is food less than 5? Then we check, is food less than 5 times worker? Then we check, is food less than 5 times workers? 7 is less than 50? Yes. Ants to cull becomes 2. Is 2 greater than 10? No. So we cull 2 ants. Another scenario where food level is 70 and there are 10 ants. Is food 0? No. Is food less than 10? No. 70 is greater. Is food less than 50? No. 70 is still greater. Ants to cull stay 0. And the nest is healthy. So queen reproduction logic runs. And for reproduction, there's a 50% chance of a new ant, and within that, a 2% chance of a new queen ant. So the overall probability of a new queen per stage is 1%. Now the movement logic for the worker ant. This is where the magic happens. The 3 cases checked in order. Case 1, the ant is carrying food. It just heads home directly. It compares its current row to nest row. If it's above the nest, the row decrements. If below, then the row increments. Same for the column. Case 2, the ant is not carrying food and index of neighbor with strongest pheromone is -1. That -1 means no neighboring cells contain any pheromones. And so the ant is searching blind. It calls choose random neighbor, picks a random valid neighbor and moves there using change cell. Case 3 is the ant is not carrying food and there is pheromone nearby. It uses list of neighbors dot index of neighbors with strongest pheromone to find the position of that pheromone in the neighbors list and then moves towards it. And those are the three rules. The entire emergent colony intelligence comes from these three conditions applied to every worker ant at every single stage. One more key method is the update ant's pheromone in cell. This is called when an ant that's carrying food moves through a cell. It loops through all existing pheromones. If it finds one at the same location as the ant, and pheromone belongs to this ant with the same ID, it calls update strength to refresh it back to full strength. Then it returns immediately. If it loops through everything and finds no matching pheromone, it means that this ant is blazing a new trail, creating a new path it hasn't walked before. So it appends a brand new pheromone object to the list. This is why established routes get stronger over time. Every ant that walks them refreshes the pheromones rather than creating duplicates. Part 4. The code has bugs and AQA knows that it has bugs. So the preliminary material literally says that understanding these bugs is important both for the theory questions and the programming task. Bug 1 is the counting problem. In nest.advanced stage, the variable ants in nest count is incremented for every worker ant that belongs to this nest. But the culling loop then selects from ants, which is the complete list of all ants across all nests in the entire simulation. The while loop inside the culling for loop does try to filter. It keeps picking random positions until it finds an ant belonging to this nest. But it's still selecting from the global ants list, which is insufficient and can cause issues in simulation 4 with 2 nests. One nest could potentially influence culling decisions for the other. The second bug is the number of queens counter inaccuracy. So the number of queens counter in nest has two problems. First, when a new queen is born in the reproduction section, number of queens is incremented. But because of the counting bug above, when a queen from another nest gets randomly culled, the nest's counter does not decrement. Over time, with multiple nests, queen count becomes unreliable. Bug 3 is the no input validation. So if you type FOGUR instead of the number 4 when asked for the simulation number, it crashes, giving you the value error. If you type 7, then the if-elif chain just falls through and simulation parameters stay empty. And so simulation gets called and crashes with an index error. Due to this, the program is not robust because it doesn't validate input for either correct data type or the correct range. The fix is to use a try except block, catching value errors with a while loop, running until valid input is received. Bug 4 is the confused user. So when first prompted, the user just sees enter simulation number 1, 2, 3, 4 with no description of what each simulation does. They don't know whether to pick 5x5 or 10x10 grid, how many nests, or anything at all. The fix is adding a display simulation choices function. Bug 5 is that the food is finite. Once food on the grid is eaten, no new food appears. In every simulation, the ants will eventually consume all available food and die out. The simulation does not model any food regeneration, and this is a design limitation. Not necessarily a coding bug, but it means that all simulations end the same way, with the population collapsing. Bug 6 is the pheromones backfiring. An ant returning to the nest drops pheromones. Other ants are attracted to those pheromones and move towards them. But an ant that just picked up the last food from a cell also drops pheromones on the way back home, pointing to a now empty cell. Other ants follow those pheromones, arrive at an empty cell, finding nothing, and get confused. Additionally, an ant's own pheromones from its previous trip might attract it back towards where it already was rather than towards the nest. The code does not distinguish between my pheromones and someone else's pheromones when deciding to follow a trail. Part 5, extension tasks. Extension 1 about the exhausted food pheromones, and then task 6 about flying ant day. So extension 1 asks you to solve the pheromone backfiring bug by creating a second type of pheromone. When an ant picks up food from a cell and that cell now has less than 10% of its original food remaining, instead of laying the normal pheromone on the way home, it lays an exhausted pheromone, which decays 4 times faster. So let's break it down. First, we need to create the new pheromone class. And this is the easy part. So we're going to write something like this: class exhausted pheromone. And then you have your constructor method with the required parameters: row, column, belongs to ant, initial strength, and decay. The exhausted pheromone class inherits all the attributes and methods from the standard pheromone class. So you start off with instructor, which takes the standard parameters, and then you modify the decay rate. So you're going to call the parent constructor super bracket dot init, and then your new parameters, with only the decay changing to decay times 4. By calling super.init, It initializes the object using the parent class's logic and setting its location, the ant it belongs to, and its initial strength. But then obviously you multiply the original decay rate by 4. And the second part is the condition, which is slightly trickier. So you need to put the less than 10% food check. So you need to put the less than 10% food remaining check. Let's look at the advanced stage in simulation. So the food pickup section is where an ant picks up food. After the food is deducted from the cell, current cell.update food in cell takes away the food obtained. So you can check how much food is left. But wait, to know if it's less than 10% of the original amount, you need to know what the original amount was. The skeleton code does not track the original food amount. You have two options. You can either store the original amount in the cell class, which is quite clean, but it would require modifying the cell. Or you can use a heuristic like less than 50% food remaining as a proxy for near exhaustion. So the question says less than 10% remaining, and the cleanest approach would be to add an original food amount attribute to the cell class. So we're going to go to our cell class. The cleanest approach is to add an original food amount attribute to the cell class. So we're going to add the new attribute self.originalFoodAmount, set it to 0 in our cell class constructor. And then in our cell.updateFood in cell, we're going to modify the update food in cell with an if statement to set the original amount. So we're going to say if the change was greater than 0 and the original amount is still 0, then set the original amount to the new change. This conditional check is really essential because it only runs when the change is a positive number, meaning if the food was added. And of course, if the original amount is still 0, which ensures that it's recorded exactly once when the food source is initialized. And it prevents it from being accidentally reset if more food is added later on in the simulation. Now we need to tell the ant when to lay this special pheromone. This will happen in the heart of the simulation, the advanced stage method in the simulation class, especially right after a worker ant has picked up food. We need to calculate what percentage of original food is left. We use the cell's current food amount divided by the original food amount we just added in our cell class. And so the calculation would be remaining percent equals current cell dot get amount of food divided by current cell dot get original food. And if the current cell dot get original food is greater than 0, the if statement here is a vital safety check to prevent a division by 0. This if statement here is a vital safety check to prevent a division by 0 error if get original food is 0. If this percent is below 0.1, that's less than 10% remaining, we set a new internal flag on the ant using a method like a.setFoodSourceExhausted to be true. This tells the ant to drop the fast decaying pheromone on its return trip. Finally, we modify the update ants pheromone in cell method. This method, which was originally part of the skeleton code, previously only created the standard pheromone object if no existing trail was found. We will change this logic to check ant's new flag before creating a new pheromone. If the ant has its exhausted flag set, we create an exhausted pheromone object. Otherwise, we create the normal pheromone object. So this is the kind of thinking you should be applying in the exam. So for example, in this case, we did the 3 steps of modifying the cell, modifying the advanced stage to set the flag, and then modifying the update ant's pheromone in cell to use that flag. One of the other tasks that we're going to look at is flying ant state. This is probably one of the most complex single tasks. So the requirements for this question are 20% chance of a queen giving birth to a flying ant each time a nest's advanced stage runs. Flying ants take 3 stages to mature in its own nest. Flying ant has food capacity of 5, not 30 like workers. Once matured, it moves to a random location that does not already contain a nest, sets up a new nest at the location using the normal simulation nest parameters. The program tells the user which cell the flying ant flew to. After setting up the nest, the flying ant dies. So if you were doing this question in the real exam, what I would do is read through the full question once, make sure you've understood it, but then try and break it down where you're looking at each requirement one step at a time, so that even if you don't end up solving the whole thing, you get marks for those. So first, let's start off by creating the flying ant class. Before I show you the code, here's the approach. Whenever you're building something new like this in the exam, your first question should be, is there anything already in the skeleton code that does something similar? Because 9 times out of 10, there is. And copying a pattern that already works is of course faster. And it still gives you the marks. So that's definitely what you should be doing. So if you look at Queen Ant, it has 4 lines. Constructor takes 4 parameters, the start row, start column, nest in row, and nest in column. Passes all 4 straight to super. Then sets type of ant to queen, and that's it. So that's exactly what we're going to try and do for our flying ant. And if you look at the worker ant, same 4 parameters with the same superclass, and then it sets type of ant to worker and food capacity to 30. So that's going to be our template. Flying ant follows exactly the same pattern, same 4 parameters, same superclass, same type of ant setter, and the same food capacity. The only difference is the values and the new attributes you need to add. So we're going to have class flying ant with the parameter ant, and then in our constructor method, the parameters would be self, start row, start column, nest in row, nest in column, and then we're going to call our constructor method on the superclass with again the same parameters. The attributes we're going to have would be type of ant, which is flying, food capacity 5, stages until unit mature as 3, and then has matured set to false, which are all the attributes given to us in the question. Now we're going to need the methods for this class. We're going to start off with an advanced stage method. We're going to call super.advancedStage, which calls ant's advanced stage and then increments the stages. You would want to keep the stage counter going so that you can call super first. Then you'd add your new behavior on the top and then decrement the countdown. If it hits 0 or below, then we flip the matured flag. Then our method has matured, which is just going to return the stages. The simulation can then call this to check if the flying ant is ready to fly. You need to make it public so simulation can access it. Then our method choose cell to move to. You need this because the ant base class declares choose cell to move to as a vital method. It's called on every ant during simulation advanced stage loop. If you don't override it, Python folds back to the empty base class version, which is fine, but writing it explicitly with a comment makes your intention clear to the examiner. Now regarding the 20% birth chance in the nest.advanced stage, this is the healthy nest reproduction section, which already exists. So when the nest has plenty of food, the queen gets a 50% chance of giving birth, which is the R number 1 less than 50 check. And within that, a 2% chance of it being a new queen, that's R and a 2 less than 2. We're not going to touch any of that. We'll be adding a third separate random check alongside it. We know we need to put it here because the task says 20% chance of a queen giving birth to a flying ant when the stage is advanced. The reproduction section is exactly where the queen births already happened. And you know the constructor arguments are going to be the self row, self column, self row, and then self column. Because that's how every other new ant is created in this method. If you look at the existing line, queen ant and worker ant, they have the exact same parameter. Lastly, we've got the maturation and nest building in the simulation advanced stage. So this might be a little bit confusing, but essentially we've got to think about where does the fly to a new location and build a nest logic actually lives. It has to be in the simulation.advanced stage. How do I know that? Because only simulation has access to both the full nest list and to check whether a cell already contains a nest and the setup a nest method. The flying ant class itself cannot do this check. It doesn't know about other nests, only the simulation does. So you'd add this after the existing per ant loop before the nest loop at the bottom. So let's go through the new parts and the borrowed parts separately. Flying ants to remove, and then the second loop that removes the self-don't ant. Flying ants to remove is going to be set to an empty array. Then the second loop that removes from self-don't ant. This is the deletion list pattern, which already exists in the same method for the pheromones. Pheromones to delete, collects and then deletes after. Exact same structure, just different list name. We're not going to be inventing this, but literally just copying it from 20 lines above. Then is instance a flying ant. This is how you identify the flying ant specifically. You could also use a.getType of ant equals flying. But is instance is just a little bit more cleaner. Then a.has matured, that's the getter you wrote on the flying ant class, and this is why we needed it. The allowed equals false, while not allowed, random row and column, for loop checking existing nests is the pattern that already exists in the simulation constructor. Scroll up to where the code places the additional nest for simulation 4 and you'll see allowed equals false, while allowed equals false, row equals random.randint, for n and self.nest, check if same location, set allowed equals false. It's identical logic that you'll be copying. Self.setup nest at already exists, and this one method call creates the new nest object, adds a queen, and adds starting ants in nest worker ants. The task says set up with normal nest parameters as per the simulation, and set up a nest at already uses self.starting food in nest and self.starting ant in nest. So calling it handles all of that automatically. And then the print statement, the program should tell the user which cell the flying ant has flown to. Flying ant to remove.append, and then the deletion loop. So once a flying ant has set up, addresses the part where the question says once a flying ant has set up a new nest, the flying ant dies. So the deletion list removes it from self.ant. And that's it. So to summarize the task, what you write from scratch would be the flying ant class with its 3 new attributes and 3 new methods. But what we're copying from the existing pattern in the skeleton code is the 4-parameter constructor structure from queen ant and worker ant, the random birth logic style from nest.advanced stage, the allowed flag while loop from the simulation constructor, the deletion list pattern from the pheromone section of advanced stage, the setup a nest at call, which already exists. So we're just making a call. So every time you're stuck in the exam, literally just scroll through the skeleton and ask, has something similar been done already? And more often than not, the answer is going to be yes. So you just literally copy and paste stuff to get the marks. And this question was 10 marks, so easy marks. Right, so part 6 is theory questions. Section C is going to be about the theory questions and the ones where you'll be tested on whether you genuinely understand how the code works without asking you to write any new code. I put together a full doc with every predicted theory question written out and model answers for each one. The link is in the description. Feel free to download it, print it, use it as your revision sheet. But let me be clear up front, I cannot guarantee any of this. AQA is the one writing the paper, so of course only they know what would come up. But these questions are very likely. The doc has 15 questions. Question 1 would be about robustness and input validation. Question 2 would be about identifiers. Question 3 about encapsulation. Question 4 about inheritance. Question 5 about the grid data structures. Question 6 about polymorphism. Question 7 about abstraction. Question 8 is the grid index and the 1D grid. Question 9 about get indices of neighbors. Question 10 about the ant movement and the 3 scenarios. Question 11 is the main one about the nest advanced stage with 6 parts. Question 12 about abstract methods. Question 13 about pseudo-random numbers. Question 14 is a dictionary versus list question. And question 15 is OOP versus procedural programming. I list the topics for each question just in case you want to revise the topic and then treat this document as a mock assessment. Part 7 is the programming tasks, which is section D. This is the section where people would either pick up easy marks or completely freeze up. This is where you'd gain or lose the most marks in the shortest time. And I want you to make sure that you go in with the right strategy. The single most important thing to understand is that your code does not need to run to actually get the marks. I know it's important that you understand the logic, your code should be functional and everything, but you don't actually need it to work. The mark scheme breaks every programming task into tiny components. And here's what a typical 8-mark task looks like in terms of what actually gets you the marks. Mark 1 might be for adding a print statement. So that's literally 1 line of code. And then the second mark might be for adding an elif branch, which is 2 lines. And then you might get the third and the fourth mark for writing a new class with the correct class declaration and inheritance. And then the final few marks would be for creating some functions, some methods, and of course the actual logic, which would be your conditions, loops, data structures, and then obviously screenshots of that. But what I'm trying to say here is you don't have to actually understand the full question and know it A to Z to get all the marks. You can still pick up marks by doing what makes sense. And almost every single section D task follows this 3-part pattern. And almost every section D task would follow this 3-part pattern. So part 1 would be, let's say, the menu option. Add a print line to the display menu. Part 2 could be a new class or a method. And part 3 would be your logic, so iteration, conditions, list modification. Now, just like section C, I've put together a doc for you to practice the questions. Of course, nobody has the paper, but based on what topics are testable, what skills AQA always want to assess, and what question structures have appeared consistently in the past years, this should be good practice. Awesome, and that's everything. All the very best for your exams. You guys have put the work in. You know the code. If you have any other questions, feel free to drop it in the comments or email me.